In this video, we'll continue to talk about Eulerian and Hamiltonian graphs. Recall that a connected graph is Eulerian if there's a circuit through the graph that contains each edge. By definition, remember that a circuit does not repeat edges. And a graph or multigraph is Hamiltonian if there's a cycle through the graph that contains each vertex. Again, a cycle cannot repeat vertices aside from the start and the end. Determine whether each of the following graphs is Eulerian and whether it is Hamiltonian. So take a look at these examples and start to think about each one, whether it is Eulerian and whether it is Hamiltonian, and we will talk about that in a moment. Okay, let's start by determining whether these graphs are Eulerian, whether they have a circuit that contains every edge. So let's start with the graph G, and if we wish, we could just use the definition, so we could start at this vertex and start to try to make some circuit that contains every edge exactly once. And can that be done? And we see at this point, we can keep going, and we can keep going. And now we sort of have a decision point. We could go up or down, but either way, we're not going to get back to the starting vertex without repeating an edge. So this appears to be no. And actually, we had a perfect criteria for whether or not a graph was Eulerian. Recall that a graph or multigraph is Eulerian if and only if every vertex has even degree. So actually, we can also verify that this is a no for that reason. So this vertex has degree 3, this vertex also has degree 3. So that means that no, this graph is not Eulerian because it has vertices of odd degree. We could continue just using that criteria, it's pretty straightforward, and look at the degrees of the vertices. So this vertex has degree 6 because a loop contributes 2 to the degree. This has degree 2, 4, 4, 4, 4, and 4. So all vertices have even degree, so this one is Eulerian. And the graph Y, it looks like every vertex here either has degree 2 or 4. So yes, this is Eulerian. P4, well, there's vertices of degree 1, so no, those have odd degree. This is not Eulerian. And it's pretty clear that that graph would have no circuit through it at all, no circuit that starts and ends at the same vertex. This graph is not Eulerian as well because it has some vertices of degree 3. And the last graph, let's see, we do have vertices of degree 3, so this has vertices of odd degree, so this is also not Eulerian. Okay, so let's look at these same graphs and try to determine which are Hamiltonian. So which ones have a cycle that contains every vertex exactly once. So let's start with the graph G. We could start at any vertex. Let's start at this one, and we want every vertex to be included. So it looks like this is working out. We ended up at the same vertex that we started with. So yes, that's a cycle that contains every vertex. So this is, yes, this is Hamiltonian. Let's look at the multigraph M. Essentially, the multigraph part of a graph doesn't really matter for Hamiltonian. If there's extra edges between two vertices, we only care about hitting the vertices exactly once, so we'll only ever use at most one of those edges if there are multiple edges. So, we are saying this for a multigraph, but these, whatever is multi about a multigraph is essentially just extra information that will not affect the Hamiltonicity of that graph. Anyway, let's say that we start at this vertex, and we could take either of those multiple edges to the next vertex. We could take that. We can't loop around because that would repeat the vertex, but the loop is just sort of extra. It doesn't really affect anything. And we could continue to go in some cycle. There are other cycles too. That's not the only option. But yes, we hit every vertex exactly once, started and ended at the same place. So this one is Hamiltonian. Let's see this next one. We could try this out. This is going to be a no. And this is going to be a no based on the one theorem that we had about disqualifying graphs from being Hamiltonian. So we could try to make a bunch of cycles and say that none of the cycles we ended up trying worked. But if we can find some set of vertices S such that the number of components in the graph when we take those two vertices away is more than the number of vertices we removed, that graph cannot be Hamiltonian. In this case, here is our set S of two vertices, where if we take those two vertices away, there will be three components remaining. So the number of components in Y minus that set of vertices S is 3. There would be 3 pieces of the graph left over not connected to one another. And this is greater than the cardinality of that set of vertices S, which was 2. So because there's some set of vertices we can take away, where the number of vertices in that set is smaller than the number of disconnected pieces there would be after removal, this is not Hamiltonian. Okay, P4, the path on forked vertices, is clearly not Hamiltonian as well, because, there's no cycle at all. If we wanted to, we could apply this theorem again and say, hey, let's remove this vertex V. P4 minus that vertex V would have 2 components, would be broken up into 2 pieces, so that also tells us by the theorem that this does not work. The graph T, is this Hamiltonian? You could, again, try some cycles and see if they work out. So we could start here, go around, go around, go around, go around. And here we're sort of stuck. We could either go in to get that middle vertex, or we could go up to get back where we started. And if we go in to get the middle vertex, we are going to be stuck. We'll have to repeat a vertex and can't get back to our starting point. If we go up back to our starting point, then this vertex would be left, and not all vertices would have been included in the cycle. So this seems like a no, but we can actually use this theorem again. So we just have to be clever about finding our set S that makes this work. So if we pick this vertex and that vertex, U and V, then S is our set of vertices U and V. And if we take the graph T minus S, that will have 3 components. So that has 3 components, and those components will be these 2 vertices left alone up here, these 2 vertices left alone up here, and this one vertex stranded in the middle. So there will be 3 components, and there were only 2 vertices in the set S. So yes, this theorem applies, and that verifies that this is not a Hamiltonian graph. H is our last example. This is also known as the Herschel graph. And you might have tried a lot of different cycles, and you should find that this is not Hamiltonian as well. It is not Hamiltonian. There is no cycle through this graph that contains every vertex. However, you cannot find any set S such that the number of components in H minus S is greater than the size of S. So while this is not Hamiltonian, you can't use the theorem to show this. If you wanted to show that it was not Hamiltonian, one thing you could do is write a little program to test all cycles through this graph H. Since the graph H is somewhat symmetric, you could also write out like a case-by-case argument. If I start at this type of vertex and try to go through, the cycle will stop here, etc. I won't ask you to argue for why a graph is not Hamiltonian, but I did want to emphasize that there is no one criteria, no one theorem that will determine by itself whether or not a graph is Hamiltonian. So the criteria for whether a graph is Eulerian, that every vertex has even degree, that's an if and only if criteria. whereas the theorem below only goes in one direction. Let's also point out here that we can have all possible combinations of a graph being Hamiltonian or Eulerian or neither or both. So this graph G was Hamiltonian but not Eulerian. The multigraph M is Hamiltonian and is also Eulerian. The graph Y is not Hamiltonian, but it is Eulerian. The graph P4 is not Hamiltonian, and it is also not Eulerian. The graph T is not Hamiltonian and also not Eulerian. And the graph H is not Hamiltonian and also not Eulerian. So we have examples of graphs that are neither Eulerian nor Hamiltonian, graphs that are Eulerian but not Hamiltonian, graphs that are Hamiltonian but not Eulerian, and graphs that are both Hamiltonian and Eulerian.